Let's go over percentage yield calculation. So when you're talking about percentage yield, you're just talking about how much is going to be produced in comparison to what you expect to produce. So you expect, maybe for example, when you buy let's say biscuits at 20 kwacha, and these biscuits, maybe there are the 10 of them inside, and then you'll be selling each one of them at 3 kwacha. You expect to make a 30 kwacha at the end. So this is what you expect. But maybe because of losses, the customer comes and then they say, no, I just have, instead of a 3 kwacha, I've got a 2.5 kwacha. That is a 2 kwacha 15 ngwe. So maybe you'll be that lenient, you say, okay, it's fine, you can get. So you find that instead of you making the exact amount that you wanted to make, it will be much lower than that. Or perhaps you, as you are selling, you change your mind. Okay, because it is on high demand, let me say it will be at 3.5 kwacha. That is 3 kwacha 15 ngwe. You might make more than expected. So your percentage yield, you might find that it will be above 100% because you've made more than you expected. But in a case where you are selling at 2 kwacha 15 ngwe, you might find that your percentage yield is much less than what you expected. So percentage yield is just going to help you to see how much you are getting according to what you expect. So here is an example. Methanol, which is also called methyl alcohol, is the simplest alcohol. It is used as a fuel in race cars and is a potential replacement for gasoline. Methanol can be manufactured by combining gases carbon monoxide and hydrogen. Suppose 68.5 kg carbon monoxide is reacted with 8.6 kg hydrogen. Calculate the theoretical yield of methanol. If 35.7 kg methanol is actually produced, what is the percentage yield? So we have got two questions here, the theoretical yield and also the percentage yield. Now notice that, well, the first thing is the chemical reaction balanced. We can say we've got one carbon, one oxygen, but we have got four hydrogens. We only have two, so we need to balance the hydrogens by putting a 2 here. Alright, yes, now balanced. Now from here we can notice that we've been given both masses of reactants. The mass of hydrogen has been given. Suppose it's 8.5 kg of carbon monoxide and also 8.6 kg of hydrogen. So whenever you've been given both masses of reactants, then you need to determine which one is going to be the limiting reagent, which one is going to be used up first. So I'm going to use a method of first determining how much of methanol is going to be produced when we use the mass of hydrogen given, and how much of methanol is going to be produced when you use the mass of carbon monoxide given. And the first thing that we need to be able to determine is the number of moles of both reactions that have been given. So the number of moles of, first starting with hydrogen, we know that is given by mass divided by the molar mass. The mass of hydrogen that has been given, we can see that is 8.60 kg. But we don't want it to be in kg because the molar mass is given in grams per mole. So we need to multiply by 1000. Why are we doing this? We are converting from kg to grams. The molar mass of hydrogen, of course hydrogen is a diatomic gas. The mass that is on the periodic table, you multiply it by a 2 to get the molar mass, and that is going to be 2.016. Let's see what we get. So when we perform the calculation here, we're going to get the number of moles of hydrogen as 4.27 multiplied by 10 to the power 3 moles. If we don't want to write it in standard form like this, of course this is just 4270 moles. The decimal point will just move 3 times going in this direction because we are multiplying by 10 to the power 3. So we can also write it like that. And let's determine now the number of moles of carbon monoxide, which is also given by the mass divided by the molar mass. And the mass of carbon monoxide we have is 68.5. We also need to multiply by 1000 because it is also in kgs to convert to grams. The molar mass of carbon monoxide is 28.02, and this is going to give us 2.44 multiplied by 10 to the power 3 moles, which we can also write as, not in standard form, this is going to be 2440 moles. Alright, like that. Now we know the moles of hydrogen and the moles of carbon monoxide. If we use these moles of hydrogen, how much do we expect to get as the moles of what? As the moles of ammonia. I mean, as the moles of methanol. How are we going to go about this one? Well, we know that remember, we want to get the moles of this product. So I'm going to say for every 1 mole of methanol, how many moles of, let's start with carbon monoxide. How many moles of carbon monoxide do we have? Or how many moles of carbon monoxide are we supposed to use? So we are saying that for every 1 mole of methanol, we are supposed to use 1 mole of carbon monoxide. And then we need to multiply. Now, how many moles of carbon monoxide are available? Here it is. So the moles of carbon monoxide available, that is 2440 moles of carbon monoxide. So the more carbon monoxide is going to cancel the more carbon monoxide, and then we just remain with the more methanol. And this is going to give us the same value, because 1 over 1 multiplied by a number, that will just be that same number, 2440 moles of methanol. Now we go also to the hydrogen. We want to determine the amount of hydrogen that is going to be produced. I mean the amount of methanol that is going to be produced now when we use hydrogen instead of us using carbon monoxide. So we are seeing that for every 1 mole of methanol produced, when we are using hydrogen, we are supposed to use 2 moles of hydrogen from the balanced chemical reaction. And then let's multiply how many moles of hydrogen are available. We have got 4270 moles of hydrogen. So the moles of hydrogen also cancel with the moles of hydrogen, and well, this is going to give us 2.14 times 10 to the power 3 moles, which I can just write as 2140 moles of methanol. Now let's compare this. When we use the moles of carbon monoxide which are available, we are getting 2440 moles. When we get the moles of hydrogen which are available and we use them to determine how much product we're going to have, we are finding 2140 moles of product. So when you are using this method to determine the limiting reagent, you are going to consider the smallest moles of product. And in this case, we can see this is the smallest mole of product. Therefore, we are finding that what? Hydrogen is the limiting reagent. Therefore, the moles of methanol that are going to be produced is 2140. You always get the smaller one. We know the moles of methanol that are going to be produced. Now the first question is saying calculate the theoretical yield of methanol. What we want to get in this case is the mass of methanol that is going to be produced theoretically. We've determined the moles. And we know that mass is given by the number of moles multiplied by the molar mass. And number of moles in this case produced 2140 moles, multiplying by the molar mass of methanol, that is 32.04. This is going to give us 6.86 times 10 to the power 4 grams. This is as in standard form. I can convert it. This is just 6,860 grams of methanol which is produced. Now if we see the method that has been given as the actual yield is been given in kg, let me just convert this to kgs. And how is that? So we're going to multiply. We can see I've got a gram on top here. I'm going to put a gram down, and then I want to go to kg, so I'm going to put a kg. We know that in every 1 kg we have got 1000 grams, so we'll just divide this number by 1000. So the gram and the gram is going to cancel. So if we divide by 1000, the decimal point is just going to move 3 times, like that. So this is going to give us 6.86 kg. Okay, so there, that is going to be it. So now let's determine, well, for this one also the value that has been given, pardon me, this is supposed to be 3.57 kg instead of 35. It's 3.57 kg. Now the last question, what is the percentage yield? Now, how do we get to calculate the percentage yield? Well, percentage yield is given as percentage yield is equal to actual yield divided by theoretical yield and then we are going to multiply that by 100%. Remember, this is percentage. Now the actual yield you've been given as 3.57. We need to make sure that the units are the same. This is in kg. And then the theoretical is the one that you calculate from the balanced chemical reaction. It is 6.86 kg and then multiplied by 100. So because it's a percentage, the kg and the kg is going to cancel out, and we're going to find 52.0%. So this is going to be the percentage yield in this one. Thank you so much for watching. Hope this was helpful, and if it was, please be sure to subscribe. Stay blessed.